Find the domain and range of G, where G is given as follows. The first thing we need to do is to recall what the meaning of domain and range is. And so if we recall this, we know that the domain is all possible input and the range is all possible output. We will start with the domain. So we're looking at the domain of G, and we would like to find out what this domain is. Now, usually the question is, what values can we not input? What values will be problematic for this function? Are there any singularities, like, for example, 1/0, or anything of the sort? And the answer here is no, there isn't any. The domain is actually any finite number, which is between -infinity and infinity. In other words, there are no problematic points, so to say, and any value you can put in for x, it will give you an output, which is defined correctly as it should. So that is not too difficult, and it's not too difficult to see either, because we have the graph for e to the x or e to the minus x. I mean, this is more or less a variation of e to the x. A bit extreme, but the characteristics of the exponential function are the same. And the exponential function is actually defined for all values x, for all of the x-axis. And so we don't really have a problem with any of the points. So that's enough talk about the domain. We can continue to talk about the range of G. And this can be a little bit more tricky. First, we need to make a certain observation. And this observation is that we can rewrite G as follows. And what I want to emphasize here is this function in the middle. I just use the laws of exponents. And so this is just distraction. It's just noise. But the main thing you should be focusing on is the pure function e to the minus x squared. And we would like to look at the behavior of e to the minus x squared. Now, going back to the graph, I would like to clarify a certain thing about e to the x. And that is that e to the x is an increasing function, which means that if I go in the positive x direction, I will find a positive displacement in the y direction. That is what it means for a function to be continuous. To be increasing. So, in other words, if y is greater than x, then e to the y is greater than e to the x. This also obeys our intuition in the sense that e to the third is greater than e squared, and e to the 10th is greater than e to the 9th. If you multiply a positive number, which is greater than 1 by itself 10 times, it will be bigger than the same positive number multiplied by itself, let's say 7 times or 8 times or 9 times, and so on, as long as it is greater than 1. So it obeys our intuition, it is good, and this is a good step towards making some interesting conclusions now. Back to the behavior of e to the minus x squared, we notice that e to the minus x squared is actually decreasing. And that is due to the minus sign mainly. But in full generality, if this function is decreasing, then the problem really is with minus x squared, which means that if x increases, then minus x squared is decreasing. This is obvious. So this is also a decreasing function. And I'm talking about the exponent itself. If I increase the value of x, I get a decreasing values. And this is mainly due to the minus sign, but also due to x squared, which is, so x squared is always greater than 0 or equal to, but then with the minus, we have an expression that's always less than or equal to 0. I think that makes sense, at least on a superficial level. And so the key to understanding the behavior is noticing that when we increase x, minus x squared decreases. And when minus x squared decreases, e to the minus x squared also decreases. Or maybe I'll be more general. So when this box decreases, then e to the box also decreases. This is what I really want to emphasize. Whatever is going on in this box, if it's decreasing, then e to the box is decreasing, and vice versa. This is just by what we have here, and just by looking at the graph. Okay, so when we increase x, e to the minus x squared decreases. That's a problem. So it's decreasing, it's going down and down and down. But is there a point at which it starts from? Before it starts descending, before the values start to decrease rapidly, actually exponentially? And the answer is actually yes. Since for any increase in x, we get a loss like this, we would like to minimize the loss. So we would like to find the maximum. So, and my question now is, which x gives a maximum for e to the minus x squared? It is the same x which gives us maximum of minus x squared. Because if we maximize the exponent, we will maximize the whole expression. This is guaranteed by the increasing property of e to the x. I hope this is clear. And then, how do we maximize this? Well, this is not too difficult. So this is a decreasing function. All the values are negative, except for one value which is not negative, which is 0. So x is equal to 0 is a maximum. Okay. And now back to the range of g we still would like to find. If the maxima is at x is equal to 0, then the maximum value is attained there. Now, 0 is in the domain, so the maximum value actually, so let's actually first compute the maxima. So the maxima is going to be equal to g of 0. So g of x is equal to 0, which is going to be e to the minus 13 times 0 plus 7. Well, minus 13 times 0, that's it. And then e to the 7. Since x is equal to 0 is in the domain, then this is in our range. And this is the maximum value we can attain. So there will not be any values that exceed e to the 7th. And this is a closed interval, which includes this point. And what is the standard minimum for the exponential function? Well, it cannot be a negative number, because at the end of the day, this is a positive number. And you multiply a positive number by itself in any certain way, you'll always get a positive number. So this value can never be negative. It is asymptotically going to 0. And if you would like me to roughly draw the graph for e to the minus x squared, it actually has a nice graph, which I believe looks like a bell. And it decays very fastly. So maybe if I remove those signs, or maybe I just move them to somewhere else, maybe here, then the graph of so this is supposed to be a bell curve, but my drawing skills are really not helping me. So this is the graph of e to the minus x squared. So you can imagine a symmetric this is more symmetric than it's very good. So this is how it looks like, and it decays at the ends because the axes get very large in magnitude, and then the maximum is, well, it's not attained at 1. Here it is attained at 1 for this function, for the pure e to the minus x squared function. But for our example, it will be attained for e to the 7th. We have to go find e to the 7th and draw this extended bell shape. So you multiply a graph generally by a constant, you just scale it up. So it doesn't affect the shape, it just scales it. So this is on a smaller scale, you could say. And if you are prepared with this machinery, and then you are ready to solve all the other problems of this type, all you need to do is just to be careful and to carefully analyze your function and see what maximas or minimas you might find out. And in our case here, e to the minus x squared is a famous example of such a function.